Hello everybody. Today we start with a new chapter in physics, that is chapter number 10, Magnetism, for ICSE standard 10th, standard 9th. We are referring to Concise physics textbook. Now the chapter is Magnetism. So first of all, if we talk about the history of magnetism, it is such that it was a natural magnet which was initially in the place called Magnesia. The stone was found and a shepherd found it, and accordingly people came to know that such a kind of a natural material is available which has got the property to attract iron, and that is basically the discovery of magnets. So the first known magnet were the piece of lodestone, so it was called as lodestone, and an ore of iron oxide Fe2O3 found in large quantities in Magnesia. So in Magnesia, which is in Asia Minor, so Magnesia was having a large quantity of this particular kind of stone which is called as a lodestone. This ore was found to possess two properties. First, it attracts small pieces of iron, and second, it sets itself along a definite direction when it is suspended freely. So the two things what we understand about magnet is that first thing is that it is having a property to attract iron. Okay, iron is going to be attracted with it. So lodestone attracts iron, that is the first property. And secondly, then when it is freely suspended, it is going to rest in a particular direction. So that is when suspended freely, it is going to rest in a definite direction. The Chinese earlier than 2050 BC, 2500 BC, used this piece to guide their boats. The pieces of lodestone found in nature were later on called the natural magnets. The word magnet has been derived from Magnesia because of lodestone present in Magnesia. That's why magnet was a name which was derived from the word Magnesia. The natural magnets are found in quite irregular and odd shape. They are not magnetically strong enough for use. Therefore, for different uses, artificial magnets are prepared from iron in different convenient sizes and shapes, such as bar magnet, horseshoe magnets, magnetic needle, magnetic compass, etc. So the lodestone, which is found as a natural magnet, does not have that much amount of magnetic strength. The strength of the magnet is not so high. That is the reason we use magnets which are artificially made, which can have a different kind of a strength also. You can vary the strength also. So accordingly, the magnets which are used by us, they are not natural magnets, but they are artificial magnets which are made based on the shapes what we want. Like for example, the common ones are the bar magnets or the horseshoe magnet, or it is the magnetic needle or magnetic compass. So these are certain examples of the magnets. If a magnet is suspended with a silk thread such that it is free to rotate in a horizontal plane, it sets itself always pointing in the geographical north-south direction as shown in figure 10.1. Depending on the direction in which an end of the magnet rests, its polarity is named as north or south. So yes, if I don't know that this magnet has got any poles mentioned on it, in that case what I'll do is that to know that what it is, which is the north and which is the south of this magnet, I'll just suspend this freely by a thread, silk thread, and then I'll allow it to move around, and then free movement is there. And when it comes to rest, suppose it comes to rest this way, then I know that this is if this is the north direction, I know that this is the north and this is the south. And if it is showing this way, and if this is the north direction, or maybe this is the north direction, I'll mark this as north and this is south. So accordingly, we can mark the north and south directions on the magnet by suspending it freely by a silk thread. And another important thing about the magnetic property is that two like poles, both north poles or both south poles, repel each other, while two unlike poles, one north pole and one south pole, is going to attract each other. So that's why it's the same thing as what is there in the charge, that like charges are going to repel and unlike charges are going to attract. Similarly, Unlike poles over here, the north pole and the south pole are going to attract each other. So if I got two magnets such that ये अगर north pole ये भी north pole है तो ये दोनों पास में आएंगे तो ये repel करेंगे. Okay? They are going to repel each other. They are not going to attract each other. But when it is this way, that this is south and this is north, they are going to attract each other. So the attraction will be there between two opposite poles, whereas the repulsiveness will be there between two same poles. So in the if the poles are same, that is two north poles are going to repel each other, two south poles are going to repel each other, but one north pole and one south pole are going to attract each other. So these are the main two properties of magnet. So the two main properties of magnet is that they are going to attract the iron pieces. At the same time, they are going to attract unlike poles, and like poles are going to repel each other. And the second condition is so first point was about the attraction and repulsion, and the second point is that when freely suspended, the magnet will always be resting in the north-south position. So these are the two very important properties of the magnet. Now, induced magnetism, magnetism induced by a bar magnet on a magnetic material. So it is seen that when a magnet comes in contact with the iron piece, first of all what it does is that it is going to magnetize that iron in such a way that an opposite pole is going to be formed in the near end. So अगर ये एक magnet है, if I bring this another iron piece over here, it will be seen that अगर ये north pole है, तो it will generate a south pole here so that it attracts each other. And then there is a north pole formed here, and then the north pole will do another, and it's this way there will be induced magnetism. So this is called as induced magnetism. So when an unmagnetized bar AB of a magnetic material such as a soft iron or steel is placed near or in contact with the magnet as shown, the bar AB becomes a magnet. So when a iron rod AB is taken in contact or made to come in contact with a magnet, then it will find that the iron bar AB becomes a magnet. That is, it acquires property of attracting iron filings when they are brought near its ends. If the magnet is now removed, it is seen that nearly all the iron filings which have clung to it falls down. That is, the bar AB loses its magnetism. Thus, the bar of a magnetic material behaves like a magnet so long it is kept in contact with the magnet. The magnetism so produced is called as induced magnetism. Thus, we define induced magnetism as the temporary magnetism acquired by a magnetic material when it is kept near or in contact with a magnet is called as induced magnetism. So, induced magnetism is a temporary magnetism which is acquired by a particular magnetic material when a magnet is kept near the material or it is in contact with the material. So that's called as induced magnetism, a very important definition which you need to learn by heart. The process in which a piece of magnetic material acquires the magnetic property temporarily is in presence of another magnet near it is called as magnetic induction. So induced magnetism is the property, whereas the process by which a magnet gets induced is called as magnetic induction. So the process by which a magnetic material gets converted becomes a magnetic temporarily is called as magnetic induction. If polarities at the end A and B of the bar AB is tested with a compass needle, it is found that the polarity developed at point A is north, opposite to the polarity of the magnet near end A, and the polarity of B is south, that is similar to the polarity at the end of the magnet near the end A. Thus, a magnetic pole induces an opposite polarity. So main thing is that the magnetic pole is going to, यहाँ पे ये north है तो यहाँ पे क्या बनेगा, यहाँ पे south बनेगा, यहाँ पे north नहीं बनेगा, यहाँ पे north है तो ये south बनेगा, and that's why there is attraction over here. Okay. Similarly, when this is north or this is south, and if this is south, this is north. Okay, so that is why you will find that the near end gets the opposite polarity and the farther end gets the same polarity. So magnetic induction में what happens is that the near end of the magnetic material is going to get the same polarity. Sorry, near end gets the opposite polarity, whereas the far end gets the different polarity, same polarity. Thus, the magnetic pole induces an opposite polarity on the near end and similar polarity on the farther end of the iron bar. Now we see something very important, and this phrase is very important because they ask you as a question, then explain the meaning of this phrase, that is, induction precedes attraction. Now it will be seen that suppose I take this magnet, okay, and I get this particular kind of material, magnetic material. Now, so what will happen is that before this particular magnet can attract this thing, what is going to happen is there will be induction taking place over here, wherein there is an opposite polarity to this formed over here, which will give the form of attraction. The attraction over here between this and this is because this particular magnetic material has got induced magnetism in it. If there would have not been an induced magnetism over here, this material of attraction, this magnetic property to attract the metals would have not been possible. So that's why we write over here that induction on that is magnetic induction on this thing precedes attraction. That is, before it is attracted, this is going to first get induced magnetism. Okay, so that's an important kind of a thing over here, that is induction precedes attraction. Now we can explain how an ordinary piece of iron is attracted towards a magnet. When a piece of iron is brought near one end of the magnet, or one end of the magnet is brought near the piece of iron, the nearer end of the piece acquires an opposite polarity. You can see that the nearer end of that magnetic material acquires the opposite polarity of the by magnetic induction. Since unlike poles attract each other, therefore iron piece is attracted towards the end of the magnet. Thus, piece of iron first becomes a magnet by induction and then it's attracted. So first there is an induction taking place and only then the attraction of the magnetic material by the magnet takes place. In other words, induction precedes attraction. So this is the very important sentence over here, that induction precedes attraction. Another important sentence over here is the induced magnetism is temporary. Now it will be seen that suppose I have got a particular magnet and I get a few number of nails, and this will get connected here, this gets connected here, and so on. There is a long chain of this thing. So if this is a magnet and these are some pins which are getting connected end to end over here like this. So this becomes the opposite polarity, this becomes same as this one, and then this gets opposite and this gets ऐसे करके not so. So it will be seen that the figure could be something like this, that this is a magnet over here, and due to this north pole over here, there will be induced magnetism. से वो pin जो है उसका यहाँ पे south होगा, यहाँ पे north होगा. Again यहाँ पे another pin which will have a south over here and a north over here. Again a pin which will have a south over here and north over here. So accordingly there will be a form of a chain of this particular pins connected to this magnet. Now suppose if I just remove this magnet from here, it will be seen that all of these pins are going to fall down. So ये क्यों गिर जाएंगे? Because the original magnet which was inducing the magnetism to the nails has been removed. So that means that till the time the magnet is present over there, the pins act as a magnet. The moment the magnet is removed, the pins no longer have their own magnetism, and that's why we can say that the induction से जो magnetism मिला है, okay, the magnetism which we have got through induction is a temporary thing. It is not a permanent magnet. So that's why I see that if one pole of a bar magnet is brought near the small iron nails, they form a chain of nails as shown in the figure 10.3. The reason is that the bar magnet by induction magnetizes an iron nail which gets attracted by the magnet and clings to it. This magnetized needle nail magnetizes the another nail near it by magnetic induction and attracts it. This process continues till force of attraction of magnet on first nail is sufficient to balance the total weight of all the nails in the chain. So till the time it is able to take the load, the magnetism is strong enough that it can hold the number of chains, the number of nails over there, it will keep on happening. But movement, then what happens? Now holding the upper piece, iron piece in position by finger. So अगर वो nails है उसमें अगर मैं ऊपर का part change किया, so यहाँ पे first this is the magnet and this is the first nail over here. So if I hold this nail and I remove this thing, right? So that is what I am doing. Now holding the uppermost nail in position by the finger, if magnet is removed, we find all the nails fall down. The reason is that on removing the magnet, the uppermost nail loses its magnetism. So all the other nails also lose their magnetism. They get separated from each other. And they all fall down due to the force of gravity. This shows that magnetism acquired by induction is purely temporary. Okay, this proves that the magnetism which they acquired by the magnetism acquired by induction is purely temporary. It lasts so long as the magnet causes induction, causing induction remains in its vicinity. So till the time the magnet is there in the vicinity, you are able to get the magnetism. Once it is removed, the magnetism is lost. So induction is going to be there only temporarily till the magnet is present. The moment the magnet is removed, the induction also is gone. So that was about induction and induced magnetism. Now we will see further about the lines of magnetic field. Now this is a very important part of the chapter because these are based on, now the whole chapter as such is based on the lines of magnetic field. So that's why we come to this particular point wherein the magnetic lines of force or the magnetic field lines are talking about. So it is seen that if you take a magnet over here, now this particular magnet, there will be a north pole and a south pole, and traveling around over here will be imaginary lines like this. Now these imaginary lines are such, they start from the north pole and are traveling towards the south pole outside the magnet, and at the same time they will be traveling from south pole, just a minute. So they are traveling from north pole to south pole outside the magnet, and they will be traveling from south pole to north pole inside the magnet. So this is how the magnetic field lines. So these lines which are there, so whenever any particular magnetic material is there within this field lines, then the induction would take place. So this is the field lines of a magnet. So let's see what are the properties and the different things about the field lines of the magnet. If a magnetic compass is placed on a table, it is found that its needle rests in a geographical north-south direction. But when it is placed near a magnet, the needle swings and then rests in some other direction. As the compass is placed at different positions around a magnet, the direction in which the needle rests changes such that its one end always points towards the nearer pole of the magnet. This behavior of the needle is due to the influence of the magnet near it. The region in which the compass gets influence is called as the magnetic field of magnet. So it's this way, that if I have this magnet and if I got a magnetic compass, so when I bring a magnetic compass over here, so it will not show. Now suppose this is the north pole, so it should actually show me the north pole like this, but it will not show this way, but it will be showing me something like this, will attracted towards this part. And over here also it will show me something attracted to this part. Over here it will show attracted to this part. So it is going to be such that the magnetic needle will always be showing me not showing me the right direction, and not showing me the complete north-south direction, but instead it is going to be such that it is much more attracted towards the poles of the given magnet. So this is because the space around the magnet has got some field that is, it has got some particular kind of magnetic field which is affecting the other magnets over here. So that is why we define it as the space around a magnet, okay? A space around a magnet in which the needle of a compass rests in a direction other than the geographical north-south direction. So when a particular needle does not rest in a north-south direction, but it is resting in any other direction other than north-south direction, then we know that it is in in contact, or not contact basically, it is in the vicinity, or it is in a space around another magnetic field. So that's why it is this particular field around a magnet is called as magnetic field of the magnet. So the space around a magnet in which the needle of a compass rests in a direction other than the geographical north-south direction is called as magnetic field of the magnet. As the distance of the point from the magnet increases, the effect of its magnetic field decreases. So if I see that, अगर ये यहाँ पे से थोड़ा मैं दूर कर दिया, if I put it over here, then I will see that it will now show me the north-south direction properly. Why? Because the field lines are going to be there only up to a certain point. उसके बाद में it doesn't have the capacity. So if the moment I make it I take it more and more away from it, I will see that the field of the direction, or you can see the deflection and the needle is going to be changing. So because it will not show that much amount of difference over here. So you can see that as the distance of the point of the magnet increases, the effect of its magnetic field decreases. Now magnetic field is a vector quantity because it has got a particular direction. I told you that it is direction from north to south. So that's why it is a magnetic field is a vector quantity. The magnitude of the magnetic field at a point is measured by the force which a magnetic pole placed on that point experiences when the direction of the magnetic field is a direction in which the needle of the compass rests when it is placed at that point. So when a needle is placed at that point and the force with which it is attracting that particular needle towards itself is the magnitude of the force of the magnetic field, and the direction of course is the north-south direction. So if we place a magnet below a sheet of stiff paper or a glass plate and spread some iron filings uniformly over the glass plate, then on tapping the glass plate gently, the iron filings arrange themselves along the circular curved lines as shown in the figure 10.4. The reason is that due to magnet, each piece of the iron filing gets magnetized by magnetic induction and experiences the force due to the magnet and arranges itself along the curved lines. The curved lines are called the magnetic field lines. So yeah, when we take a particular, suppose I take a glass sheet or I just take a paper sheet and place a magnet in the below this thing. I'm putting it dotted so that you can understand that it is below the thing. So this is the magnet, and you have placed some iron filings over here. So if I place certain amount of iron filings over here, sprinkle some iron filings, and then I tap this paper, you will find the iron filings will be taking this particular shape over here. So the iron filings will be arranging itself in circular manner like this. Now this circular manner in which it is going to be placed is nothing but the magnetic field of that particular magnet. So that's how it has been seen that the magnetic field lines are going to be traced with the help of an iron filings placed on a paper. So when a compass needle is placed at any point in a magnetic field, its needle rests along the magnetic field lines. An arrow is marked on the magnetic field lines from south pole of the needle to its north pole. The arrow indicates the direction of the magnetic field at that point. Thus, the magnetic field lines is a continuous curve in a magnetic field such that tangent at any point is gives the direction of the magnetic field at that point. So the direction is nothing but tangential at any particular point. So when I'm taking any particular point, so you can see if I take this particular point, the direction is this way. If I take this point, the direction is this way. If I take this point, the direction is this way. So at any point, the direction of the magnetic field is tangential to that point. Okay, so it is always the magnetic field, it will be tangent at a point of it in the given direction of the magnetic field. We now come to the very important part, and that is the properties of magnetic field lines. So there are totally 7 properties of the magnetic field lines. So let's see them one by one. The magnetic field lines have following properties. First, they are closed and continuous curves. So they are closed and continuous because they are going to travel inside also. That's why they are going to be a closed and continuous curves. Second, outside the magnet, they are directed from the north pole towards the south pole of the magnet. So outside the magnet, they are going to travel from north pole to south pole, and inside the magnet, they are going to travel from south pole to north pole. So that was second point. Third point, tangent at any point on the field lines gives the direction of magnetic field at that point. So we just understood this way, that the tangent at any point on the magnetic field will give the direction of the magnetic field. Right? So magnetic field lines is always tangential to that particular point. Point number 4. They never intersect one another. If two magnetic field lines intersect, they would be two directions of magnetic field at that point, which is not possible. So figure 10.5 shows two magnetic fields lines PQ and PR intersecting each other at point P. It would mean that if a compass needle is placed at that point, north pole of this needle will point in two directions, PQ as well as QR, simultaneously, which is not possible. So when you have got two magnetic field around, they will never intersect each other, because if they are able to intersect each other, उसका मतलब क्या हुआ? This is going from its north and south, this is going from north and south. उसका मतलब है north इधर भी हो इधर भी है, वो possible नहीं है, right? So that's why you will find that always whenever the magnetic fields are coming close to each other, they will compress over there, but they will never intersect each other. Okay. Point number 5, they are crowded near the poles of the magnet where the magnetic field is strong and are far separated near the middle of the magnet and far from the magnet where the magnetic field is weak. So it is seen that the magnetic field is strong near the poles over here and over here, whereas over here, the central part over here, the magnetic field will be far off and will be much weaker. So that's why we see that the magnet, they are crowded near the poles of the magnet where the magnetic field is strong and are far separated near the middle. They are far separated near the middle of the magnet and far from the magnet where the magnetic field is weak. Point 6. Parallel and equidistant field lines represent a uniform magnetic field. The Earth's magnetic field is in a limited space is uniform. So when you see that the magnetic fields lines are something like this, so if these are the magnetic field lines, then it will be understood that these magnetic field lines are the uniform magnetic fields, which are normally about for a very big magnet. Like for example, the Earth's magnet is going to have a magnetic field around the Earth, which will be of uniform magnetic field. And lastly, the 7th point, and that is they behave like a stretched elastic rubber string. So as I told you, whenever they come near each other, they are going to compress over there, and that's why we see that the field lines, magnetic field lines, act as a stretched rubber string. Okay, they are always going to stretch rubber string. That's why they can easily compress itself or expand itself because of the elastic kind of a rubber kind of behavior of theirs. So that is about the properties of the magnetic field. We now move on to the magnetic field of the Earth, that the evidence of the existence of the Earth's magnetic field. So, but I'll take it in the next video.